So I'm here today to talk to you about reinforcement learning, and the goal of this is really to give you an overview of the topic. I know there was a training session that took place and there's been some other talks on the subject. If you know it like the back of your hand, you're welcome to stay, but this is going to be really about giving you the fundamentals so you can understand how to approach the topic if you want to learn more later. It's kind of a thing I like to do. Who am I? My name is Melanie Warwick. I work for Google. I'm a developer advocate, and I advocate for machine learning as well as a Google Cloud Platform, sometimes together, sometimes separately. So, like I said, something that I've done over the last few years is I have a habit of taking certain topics, especially ones that are kind of top of mind, and I like to try to break them down and make them easier to consume, to start out in. And that's the goal for today. So when you talk about reinforcement learning is really like it sounds. You know, it's this idea of being able to generate some type of performance based off of a reward. That's the goal, the ultimate goal. You want to maximize whatever your reward is, and you want the computer, the technology, the software to be able to come up with a model, a framework in order to operate and maximize its rewards. And you can think about it almost akin to, you know, as a person, as a human, you want to maximize the dopamine, right? I get a dopamine push when I eat chocolate. Everybody has their thing. So we will work towards maximizing our rewards. Sometimes I'll go out and get chocolate ice cream every other day. So to maximize rewards and to explore this space from a technology standpoint, a really popular way to do it is to explore it with games. And back in 1992, the TD Gammon program was built to be able to play backgammon and to find a way to play it more effectively than humans, or to play it as effectively as humans and sometimes more effectively. And what was really great about this is that it was able to find ways to play that humans wouldn't have necessarily thought of. It sort of helped identify new and more strategic play positions. And more recently, AlphaGo, of course, last year was beating Lee Sedol, one of the leading players in Go. And that's another situation where what was really fascinating is, you know, seeing how reinforcement learning was applied. You saw these moves that it would play that a human would have discounted, but when you played out the full game, you saw that losses it would take led to bigger gains. So games, I know games tend to make this subject seem a little less credible, a little less solid as a solution that you would really apply. But the reality is that games are perfect for being able to explore this algorithm, to be able to really sort of condense down a specific defined space and see that you can get some kind of reward and see that it is a successful algorithm to apply. And then you can start to have conversations and think about, what do I do with more of a real-world solution? And so a great example is when DeepMind took reinforcement learning and applied it to analyzing Google's data centers and being able to see ways to optimize the performance of the data center so it reduced energy use for cooling by 40%. Like, that's a real world application. That's when you start to say, hey, maybe I can actually use this. Now, I know at the very beginning of the conference, Andrew Ng had mentioned that it is not necessarily seen as being as impactful as deep learning, and that's extremely true. You know, there's still a lot of work to be done to see where reinforcement learning can be applied. And the reason why is because data and the time to really apply this algorithm effectively is still a big hurdle to overcome. But it does have potential uses, potential applications. So what I want to do is take you through an understanding of, I want to take you through an understanding of how to break this down. And specifically, I'm going to give you the core components and then talk about the algorithms, some of the algorithms you can apply. Because let me just take a second and say, there's a good amount of information out there that will help step you through what reinforcement learning is. And it's extremely, there's a lot of depth to it because it's a very complex subject. But I'm going to try to make it simple right now, or as simple as I can. The components, you have an environment and you have your agent, okay? So your environment is where you're playing out, whatever you're going to play out. And your agent is your software. And the agent will exist in certain states. It starts out, it takes a step, it moves into a new state. And it takes action. So it took that step, that's an action. It has whatever state it's in, certain number of actions that it can work with. And in the new state it moves into, it has a number of new actions it can choose from. And to make it work in this environment, you're giving it a goal. You're giving it a reward. You're saying, this is what I want you to work for. So another component you need to keep in mind is time, horizon. This is going to also play into what you're getting, when you're getting it, what that looks like in terms of how to make this model work. So you as the agent, or the technology as the agent, has behaviors that can be controlled. And those behaviors mean it's the policies that you're controlling for. Okay? That's what you get to control for. You don't control the environment, you control the agent's behaviors, the policies. The environment is where you're exploring. It's where the agent is exploring and seeing what works for it. Usually when you review any kind of material out there about reinforcement learning, it is referred to when you talk about the environment as the MDP, or the Markov decision process. And really it's saying it's helping you work with the Markov property. And I know you're all thinking, oh yeah, we know that. Or some of you might, maybe not all of you. What that boils down to make it as simple as possible, is that where you are right now is all you need to know to be able to make predictions and estimations about where you're going to move to next, and what the value is of where you're moving to next. So when you hear anything in reinforcement learning and they keep saying MDP, 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 they're talking about environment. They're talking about the environment in which you're working in. And that environment is comprised of a reward function and a transition function. Sometimes you don't know anything about the environment. So the transition, thank you. So the environment is made up of a reward function and a transition function. And reward function I think is fairly obvious, but a transition function, this is really just saying with the states and actions that you have, this is the probability that I'm going to move from one state to the next state. So it's just a matrix of probabilities of moving from one state to the next state, and you do not control that. That's just what the environment has in existence. So if I step off the cliff, the probability is that it's probably 100% that I will hit the ground. If I open the door, there's maybe a 50% probability that I'm going to walk through it. Or I will actually be able to open the door. So there's your environment, there's your agent, and the agent has a number of states that it can exist in the environment, and actions it can take. And you can graph that out into some type of tree and say, here's all the states, here's all the actions as I explore the space. And I use this is actually a min-max algorithm, but you don't really need to know that. I use this to help explain the fact that this state action kind of graphing that you can do can allow you to understand at what point you can achieve that reward. You can think about it in this sort of tree graph to say, if I go, X direction, like, adventure game, choose your adventure game, then I will have these options and I can take this next direction and keep going down and down and down until I get to the end, and then I know what my reward looks like. That's how it will map back. And this is a great little subset in the tic-tac-toe game of how you can see where you can map out what your actual gameplay could look like based on your opponent. Tic-tac-toe, you could fully graph this out. You could understand the rewards. You could exhaustively search the space and figure out the most optimal plays. But when you start to get into something like Go, the actual number of states alone are too large to fully hold in memory, let alone do the full computations to understand and figure out what the best path is forward. So there are various techniques and approaches to be able to figure that out. What we're going to do now is just touch on some of the key algorithms that you look at when you're talking about reinforcement learning. At the end of the day, if you haven't already picked this up, what you're really going after, sure, you're going after to maximize your reward, but what you want is to maximize your behavior. You want to get the most optimal policies. That's what you are going after when you apply this algorithm. And whenever you see any of the actual algorithms that are out there, when you see it written, you'll see a star when you're referring to optimal, you'll see pi for policy. So the main functions that you're getting out of your reinforcement learning is these functions, and sometimes it's one or multiple. It just depends on what you're building out in terms of your models. When they say model, they're talking about the agent's model of the environment. When they say value function, this is the value you're achieving based on your current state and all the future potential possibility state values. And the policy, and the value, I'll come back to the value. And the policy is when you are potentially modeling the policy, the behaviors themselves. So as I mentioned, you have an environment. The agent has its own interpretation of what that environment looks like. Sometimes the agent has an interpretation, sometimes it doesn't, sometimes it'll track it. There are a number of ways you can do that. I've listed just a couple at the bottom there. When you start out, you're starting out with something simple, and you'll use something that's more like a table, literally a table of state and action pairs and rewards associated to it. Neural nets have become extremely popular with everything, and of course it's very popular in this space as a way to track your model. But like I said, sometimes you will have information on the model, sometimes you won't. And there's algorithms that allow you to work with the fact that you have, you may have information about your model and you may not. And I actually summarized this off of a slide that Chelsea Finn had done. And she's got some great content out there I highly recommend checking out. But the main thing is to understand, there are pros and cons to having model-based algorithms that you use versus model-free algorithms. And there's also pros and cons to using them together. And where this comes from is that if you are, let's see if I can make this work. So when you are the agent, you're going to start out thinking like, all right, I'm going to define a value function and a policy, or one or the other, and I'm going to guess at it. And then I'm going to act, and I'm going to get some experience. Now here's where I can either directly update my value function or my policy, or I can say I'm going to learn and add and start drawing out my model and make some plans off of that model. And the nice thing is that if you track your model, you can actually do some type of task transfer and generalization. And what I mean by that is, if I wanted to train my dragon how to screw a top onto a Coke bottle, and it learned, and then I said, now I want to take that same task and have it learn how to screw in a light bulb. Well, if I have a model, it can just reapply that to this other problem, and it will learn it a lot faster. All right, so that's one of the values of being able to use a model, and this is also the components of when they talk about planning and learning. You're planning when you're using a model, you're learning when you're not, and that's where you're doing the reinforcement learning. All right, so that's mostly what I'm going to cover around the model piece, and there's a lot of great content out there that I highly recommend exploring. And that is not going. Aha. When people get into reinforcement learning, they typically start exploring from the value function perspective. And as I mentioned, so value function is trying to understand the reward as it relates to states and spaces, or states and actions. And it's trying to indirectly identify the most optimal policies. And it will do a value as it relates to a state or state and action pair. And my clicker is not working. Let's see. My computer's not working. Oh, technology. Okay. When you start out with reinforcement learning, typically people will start with the grid world, which is basically a small environment, and it's a very condensed environment to make it easy for you to explore. And so you have a goal, you have a reward you're going after, you have a very set small amount of spaces and actions you can take, and these are the actions in each of the states. You can go up, down, to the sides, depending on where you are in that grid. And you also have the transition model. This is where you have the probabilities of, if you take this action, the probability of you moving from one state to the next. Sometimes it's exactly, you will definitely move. There's not really a probability. If you move in that direction, it's 100% probability you will move. When you're doing value-based functions, there's this approach that is taken, which is primarily known as this general policy iteration, and it's using prediction and control. And you're ultimately saying, I'm going to evaluate, I'm just going to pick policies at random to start, and I'm going to evaluate them and see how they do as I go through this grid world and get the result. And then I'm going to get a value for every single state that I was in. And I'm going to go back and update and say, these are good policies to have in those different states. And I'm going to just keep exploring and evaluating and then picking greedily the best policies and going back. And to evaluate, I'm using what's known as the Bellman equation. So this is really a fundamental part of the puzzle when you're really starting out with reinforcement learning. And what it's doing is it's helping to break down the problem, the larger problem, into smaller bite-sized pieces. So instead of trying to do the whole grid world at once, I'm picking each state and trying to understand what the value is in each state. And I'm trying to understand the value as it exists, as I stand in that state, as well as what the future values are going to look like. And so that's what the R and then the gamma combined with the PV is doing. It's saying, what's my value as I stand here right now? And what's my value as I hopefully act optimally going forward to get to the end? And then I will use this to help me evaluate. While my control side of the equation is just saying, hey, I got these values. It looks like this is the best policy. Let's keep using this policy in this state going forward. And if I go through and I'm going to explore the space multiple times, update my values multiple times, and ultimately come up with an idea of these are the best policies based on the state that I'm in to get me to the end game. There's a lot of great content out there that will help dive further into this. This is just giving you an understanding of how to start to think about it. And these value-based methods, I've given you just the high level of this prediction control cycle. The value-based methods fall into sort of certain camps. And the camps really are about how you do your updates in terms of your value function. There's the exhaustive search, where you explore the whole space, like the tic-tac-toe, or checkers actually apparently did this brute force. We map every single option, between the two players and all the values, and we find the best path forward. Versus dynamic programming is saying, we are not going to, we probably don't have a huge environment anyways, but we can map this out and do shallow updates. We don't fully go down the path before we make an update. TD learning, well, actually, before I say TD learning, let me talk about Monte Carlo. Monte Carlo doesn't want to understand the full, it's best when you have a model-free environment in terms of it's too big of an environment to explore, so it's better to do sampling. And I'm going to sample exploring the environment and continually update values based on the results of my sampling and try to kind of find a nice medium between those results. While TD learning is combining both dynamic programming's bootstrapping technique, so you don't go too far before you make updates, and Monte Carlo's sampling technique to say, I may not know everything about the environment, but I'm going to try a number of different options. With dynamic programming, there's a lot to it. And I think, actually, how am I doing on time? Great. So there's a lot to it. And this is one of many algorithms in this space. The main things I want you to understand about dynamic programming is that you are focusing on this point of, I'm trying to get a reward for every state and policy. And I'm trying to find the most optimal policy. And that's really what I want you to understand from this. That algorithm that I was showing you is really a variation off the Bellman in terms of, how we're doing the evaluation. And below that is really saying picking the best policy, okay? And this is doing it from a state perspective. I'm trying to get a value for every single state. There's also this Q value where you could get a value for state action pairs. You're going to break it down and say for every action in that state, I want to get the Q value. I want to know what my state action pair values are. And that will help me identify the best direction to go in. So there's value iteration, there's policy iteration. I'm not going to dive into policy iteration, but I want to just touch on the fact that that is in existence in this space when you're doing value-based calculations. As I mentioned, Monte Carlo. Monte Carlo is great when you don't know what your space is, but you have to have an episodic environment to work out of, meaning you have to be able to find an end and get a reward because you want the real reward based on your sampling to use that back inside of your equation. So Monte Carlo uses actual rewards from sampling, and that's key for it to be successful. While temporal difference, as I mentioned, is using a combination of I'm doing some exploration, but not fully, and I'm updating as I go, and I'm also just sampling. And so the reason why this is useful is if you, and I'm using this example out of David Silver's lectures, he was talking about how if you have a car that is in essence about to hit a wall, you don't necessarily want the car to hit the wall to find out this is a bad thing to do. If it can find there's a value that's a negative value from that experience before it hits the wall, then it wants to update it in real time. So temporal difference is great for more like an online learning experience. The other thing to note about temporal difference is this is where you start getting into cue learning. Now, you may have heard of cue learning when you've heard of reinforcement learning, and that's coming from the temporal difference area. And it is using cue values. It's just not doing the full tabular map out of your actual environment. So cue learning is played out inside of temporal difference learning. And with cue learning, you get deep cue networks. So it's really cue learning applied with a network, because everything's better with a network. All things are much better with neural nets. It's all the rage. And really, with deep cue networks, the idea is that the neural net serves as this model that you can pass in either state and action or just state, and you ultimately get out of it an action or a cue value for the state action pair, or you get a cue value per action that you have as an option for your state. And this will help you decide what action to take. And what you're doing at the end of the day with all of this is you're getting a value to help you decide what is the action I want to take. Deep cue networks came about because of DeepMind, when they were exploring the Atari games. And I think most people probably have heard about this, and if you haven't, there's some great materials out there, and you can actually play with them yourself. But they did a lot of work around Atari games and trying to help the computer figure out the most optimal ways to play these games. And they were extremely successful, and this is just one of many. There's, like I said, a lot of videos that exist out there about this. So that's where cue learning and deep cue networks fit in. So just like Game of Thrones, I think I'm going to squeeze in the rest of this at the end. Thank you. There's the value function, and the value function has been this whole thing about like indirectly figure out a value from the reward to figure out the policy. But the reality is, why not spend some time modeling the policy? And you're probably thinking, well, why haven't we been doing that this whole time? You know, certain cases call for certain measures. And a great example, again, stealing this from David Silver's lecture, is that if you played, rock, paper, scissors, there's not really a value you can ascribe to the actions that's going to make one stand out over the other. There's a little nuance to that. But for the most part, go with me on this. There's not really a value you can ascribe that will differentiate those three actions. So you have to go with the policy. And the policy is its uniform random policy. And that is a great example of where you can say, why don't we model the policy? Certain situations, it does make sense to create a model for the policy and use that to help you basically have your optimal policy. It's great, especially when you have these very complex environments that are also continuous. It doesn't have to just be continuous environments. The challenges you have with policies is that you'll have a lot of high variance, or you'll have high variance in terms of its results. So there's a number of techniques like baseline and advantage functions that are used to help you fix those variances. But it's much more efficient in terms of storage and the kind of data that you need to keep track of. When you're working with policies and policy search, you're typically working with, there's a number of algorithms you can work with, but they fall into two main camps. There's gradient and gradient free. And I'm not going to actually go through all of these, but there is great resources out there for them. Mostly I'm going to touch on the fact that, there is a really good blog post that has been out for I think a couple of years now from Karpathy, who's a well-known researcher out there, and he did this great post about policy gradients in general. And they're fairly popular when you explore the reinforcement learning space. But he was showing how with the game of Pong, you can apply a policy network. And again, this is using neural nets with basically that will model the policy. So instead of modeling the value, the value function for the state action pairs, you are modeling what the actor behavior will look like. And in this case, you're saying, the actor's behavior is literally moving the paddle up or down. It is one of those paddles, and it's saying go up or go down. And it's feeding it pixels to decide go up or go down. And the key thing to note here, I ran this actually on a server, and I ran it for like 5 days. And I'd say the first couple of days it just lost. But probably about the third day, it started to really show that it could play and win some. And by the fourth day, I think it was really starting to win on the whole. And by the fifth day, it died because I think it ran out of memory. But it was great to kind of explore with it. And it's a really simple, if you want to try something out, this is really easy to use. The code is up on, he's got it up on a gist. So I've got a link in the slides. So policy, it's good to model your actual policy behavior. And it's also great because, I've noticed in the reinforcement learning there's a sort of a tendency to go, well, why don't we just combine everything? So they have gone to this approach of saying, why don't we do a model of the value and a model of the policy and put them together? And that's where we get this whole A3C model. If you've heard of this, it's asynchronous actor-critic agent. And the idea here, it's a little bit like that GPI of this general policy iteration. What's happening is that you are still using the same thing around the value function. And there's a tendency to use TD learning, but for a critic, the critic is really the evaluator. It's evaluating the policy, and the actor is your policy model. And it's looking at what the critic provides and then using scores that it gets out of its from its model performance in the gradient search. So asynchronous actor-critic is really just iterating through and getting these two models to come together and find the optimal policy. And the other thing to note is asynchronous, right? Because there's one thing about actor-critic. Well, what's the asynchronous part? Instead of just doing one actor, doing multiple actors in multiple environments. So that's what the A3C is standing for. Sometimes you'll see A2C because it's not using multiple environments and multiple actors. And yes, this is where you could start to say, like, do we do distributed computing? And sure, you can. You don't just have to do asynchronous with this model. You can explore that with other models, but this is one that's been fairly well known and popular in the space. And DeepMind applied this to, there's other examples out there, but I like this one, where you're navigating through a labyrinth and you're trying to find apples. And the really, I think the poignant part about this is the fact that it is faster to learn. It's a faster learning mechanism in terms of finding good solutions. And that's a real challenge in reinforcement learning in general, is that they are slow to find actual convergence, slow to get to some type of result. But when you start to apply, especially when you're distributing this, you'll get solid results pretty quickly. Okay, so reviewing what we covered. We've got the model of your environment. You may or may not track that. You may or may not already have that. And you can make plans if you do have it or you decide to track it. Your value function is really allowing you to track the value based on your state or based on your state in action so that you can figure out what would be an optimal policy. Your policy is creating a model of your behaviors, and you can combine the two together to form the ultimate Megatron and solve everything. As I mentioned, convergence is a challenge. That's one of the bigger challenges in the space. Another one is credit assignment, meaning you have delayed rewards. So I showed you the grid world in the beginning. You saw that at best you have to go through 3 states at least to get to the final reward. There's a number of situations where the reward might take a really long time to get to it, and figuring out how to assign rewards back into the space so that it can decide this is the best action to take is challenging. But there's a number of techniques to explore to help you solve that problem. Exploration-exploitation is also it's a continuing issue from the value-based function side of things, because once you start to get values identified for states and state in action pairs, you have to decide how long do you keep trying other policies? How long do you keep looking at other things in case those, actions, those potential actions are better rewards for you long term? So exploring that, there's a constant sort of juggle between how long can you explore. And generalization. As I mentioned early on, models can be very valuable for planning. Taking these models, taking reinforcement learning, whatever you've learned, and being able to generalize it across other problems, having transfer learning is something that is not easy to do and is a continued challenge that they're trying to overcome. There's a number of libraries that you can explore. I've just listed a few from DeepMind and OpenAI and Facebook Research that you can definitely check out in terms of being able to try out reinforcement learning on your own. And I'm going to leave off with one more thing before I get to my very last slide, which is RoboCup. And I'll talk about that after. Oh, and I'm not going to leave off with that. Come on, we're going to play. This is very important. It's extremely scientific. And
highlights from RoboCup 2017. And now, highlights from RoboCup 2017, vastly improved by Univision Deportes commentator Luis Omar Tapia.
El amarillo 4 quiere pasar entre medias de dos volantes del equipo azul. ¿Quiere? ¿Puede? No, señor. La pelota que rebota y está tendida en la zona media. Ahora va a venir el pelotazo largo, pero el balón que vino de primera. ¡Falta! El árbitro cobre la falta de conseguir ley de ventaja. El centro va a venir en el borde del área. Ya están 5 para pegarle de zurda. Va a venir el martillazo. Le va a pegar gol. ¡Gol!
It's always great when you can use somebody else's video. Okay, so this is interesting, and I'm going to mention just a couple things really quickly about this. RoboCup has been around since 1997. The idea came about by a professor back in 1992. I'm going to forget the name of the professor, but the idea was, hey, we want to show how robots performance in robotics and show it in an interesting way. And I wrote a paper about it, and Japan was like, we should make this real thing. And then other people heard, and they were like, can we make it a worldwide thing? And they've literally been doing this since 1997. 20 years. And I think policy gradients and reinforcement learning has definitely been explored, at least for the last 10, maybe longer. But it's amazing because, we've seen these games that we've achieved so far, and the goal for this group is to get these robots beating humans. That goal is on their minds. That seems impossible. Reinforcement learning seems kind of almost impossible at times. I'm like, how do we really apply this to things? But the reality is that's very possible. And it's really weird to think about it. But especially when you see those adorable little bots, you're like, could those adorable little bots beat us? They have some really freaky ones. I highly recommend you checking out some of the other older videos too to see what this looked like. But this is interesting because, reinforcement learning, sure, we're still far off from really seeing the full value of it. There is way too much hype in this space. There's way too much hype in all of this space, frankly, in my opinion. And my goal always is to try to help bring it down to here's what you know right now. But it is exciting. It is exciting. It's exciting to think about where it can go. And it is something that is getting us closer to AI, whatever that looks like for whoever you want to ask. But it plays a role. Anyway, okay, so last points is that, I mentioned this already, but some of the key challenges are definitely and some of the things that people are really focusing some of their research on is around exploration and transfer learning. The real components I wanted you to take away is that, you take the problem, and to solve it, you're going to break it down, and you're going to try to find optimal policies for the smaller chunks to get you the overall bigger policy, optimal policy that you want to solve that problem. And that's what you want. You want to maximize your reward, but to do that, you need your optimal policy. I will be posting this deck later for sure, and I have some resources. I'll stop on this slide. These are some of the resources that I've explored that I think are great for, just when you're beginning. The Barton Sutton book is mentioned a lot, and frankly, most of the materials that I've seen sort of almost go through the Barton Sutton book in one way, shape, or form. Definitely some of my diagrams are similar to that, but most of the people out there, when I see any diagrams that they use them straight from that. And there's a great grid world example out there that you can kind of play around with if you want to try your own. Definitely check out that Pong example that I mentioned and the different repos that are out there. And of course, I've got all these references for the images that I've been using. That's it. Reinforcement learning is a little it's very overhyped, but it's got some potential. It's definitely got some potential. And check out the RoboCup. It's fun. All right, thank you.